In this video, we're going to continue to talk about entropy, and we are going to start by talking about the third law of thermodynamics. So the third law of thermodynamics states that the entropy of a perfect crystal at 0 Kelvin is 0. So 0 Kelvin is absolute 0. And what this really means is that this is our reference point. So when we say a perfect crystal, we mean an ideal system. And we need a reference point to measure other entropies against. So all other entropies are measured against this perfect crystal at 0 Kelvin. So in a way, this is our reference point. And if everyone agrees upon the same reference point, then when we speak about entropies, we're all talking about the same thing. So entropy is an extensive property, which means that it depends on the amount of substance that I have. So the more of a substance I have, the higher the entropy is going to be. So the units on entropy are joules per mole Kelvin, and this joules per mole indicates that it's extensive. So depending on how many moles I have, that will influence the entropy of this system. This little knot here depends on standard temperature and pressure, and so you'll see that sometimes, and it assumes 1 atmosphere and 25 degrees Celsius. The K, as we go along, we're going to use the Gibbs free energy equation, and we'll see that entropy and temperature are tied together. And so the Kelvin under here is going to accommodate for that. So without using hard and fast numbers, we can look at some trends in enthalpy. And we spoke about this a little bit yesterday in class. One of the trends is the phase of the substance. So the entropy of a gas tends to be greater than the entropy of a liquid, and that is greater than the entropy of a solid. And this has to do with those microstates. So there are more energetically equivalent ways for the energy to be organized in a gas than in a liquid or a solid, and that has to do with the types of energy that a gas has available to it. So gas molecules are vibrating, they're rotating, and they're moving in translational ways, so straight line movement. And because there's so many more energy types available, the entropy of the system is higher. So in general, the entropy of a gas will be greater than the entropy of a liquid or a solid. Size can also impact entropy. So generally speaking, a molecule that's larger has higher entropy than a molecule that is smaller. Additionally, we can talk about allotropes, which are different forms of the same element. So in class we talked about graphite versus diamond. Both of these are carbon, but they're different forms of carbon because of the way that the molecules are organized. That's an ugly C. There we go. C for carbon. So as an example, we saw yesterday the forms of diamond and graphite. In diamond, the carbon atoms are hooked together in a tetrahedral shape, and diamond is much more constrained than graphite. whereas graphite is sort of sheets of carbon atoms, and those can slide past one another, so it's less constrained. So the entropy of diamond is going to be less than the entropy of graphite because of that constrainment. Another factor that can impact the entropy of a system is the complexity of the system. So the entropy for something that is complex is going to be greater than the entropy for something that is simple. So if we think of an enzyme, for example, that's a very complex molecule, and it would have a lot of entropy, a high entropy value, whereas something that's a small, simple molecule would not have a lot of entropy associated with it. The other factor is dissolution, or when we dissolve something in a solution. So before we dissolve it, we would just have some solid, and the entropy of that is going to be much less than the entropy of that solid when it's dissolved in an aqueous solution. So in a solid, for example, if we think about NaCl, there are just NaCl molecules packed next to one another. I'm going to draw a bad beaker here. So if we have a beaker, what happens in solution are my NaCl molecules and atoms are going to dissociate from one another, and then I'm also going to have water molecules hanging out around them. So there's going to be a lot more entropy in that system because it is a lot more complex with the interaction of the water molecules and the sodium and chloride atoms that are dissociated from one another. To finish this assignment, please read the accompanying section in the book and take the reading quiz.